So thank you for letting me know what I'm talking about. Sometimes when you prepare talks well in advance, you're no longer sure what are you discussing. And so what I want to do today is I want to talk about some work that I've done with a bunch of students over the years at the William Small REU. There are a lot of open problems in stuff like this where if you know a lot of algebraic geometry, which I don't know, you might be able to prove good theorems. More theorems have been proven in the last couple of years than for the previous decade before that, as more people are getting interested in these biases. I discovered them back when I was a graduate student, and over time we've been able to prove a lot of special cases, but the problem is these special cases are not generic. And so because they're not generic, we may be completely misled as to what's really going on. So I'm really hoping to form some collaborations. I am at Williams College, which is essentially in the middle of nowhere. So for me, Dartmouth is actually quite close. Very happy to either come back here and work with people or to have people come down. I mentor a lot of students online. I'm always looking for graduate students who are interested in working with me, with students in the Polymath Junior program. I think there's a lot of stuff like this that would be terrific for that can be broken up into a bunch of related, easier problems that you could have students investigate and trying to build some intuition. So just as an overview, the problem with looking at elliptic curves is things are often converging at the rate of the log of the conductor. And so even if your conductor is of size 10 to the 20th on a logarithmic scale, that's really small. And so a lot of the data is going to be misleading. I have now reached the point where I think I'm now one of the older number theorists working in a lot of these problems. And when I was young, there was a lot of belief that maybe there are curves of arbitrarily large rank. And maybe there is such a thing as excess rank. And so I can see some of the slightly older people in this room nodding their head and remembering those days where now the data has finally gone far enough that a lot of these conjectures are no longer believed. And so this is always the danger. So one of my favorite examples is 40% of all integers are prime and 20% start a twin prime pair. And I am very glad right now that Carl is not listening to me prove this theorem. So I will prove this theorem experimentally. So let's look at all of the integers up to 10. And so the primes are 2, 3, 5, and 7, and 3 and 5 start twin prime pair. So 40% of all the integers are prime, and 20% start twin prime pair. If you doubt this, double the range of computation. And if you double the range of computation, everything is still true. So you would never conjecture anything based on a small set of primes like that. We have to be very careful about doing similar things with elliptic curves. And that we might think we have a lot of data when we have millions of elliptic curves, but when you consider the rate of convergence, it's very small. So I think the nicest way of saying this is the seminar organizers are willing to humor me slightly in talking a little bit about random matrix theory to just set the stage. And then I will go into, as well as I can, algebraic geometry and elliptic curves. But I want to set the stage of a situation where we can actually isolate lower order terms. So a lot of my life's work is looking at fat, thin families. I want a family that's fat enough so that I actually have an averaging formula at my disposal, but thin enough so that I might actually see some new behavior. Number theory is hard. Anybody who is a graduate student here, hopefully your advisors have given you the talks so that you know what you're getting into. Random matrix theory is much easier by comparison. You have much better averaging formulas. You have much better probability spaces to work with. It's much easier to prove results. And so I want to show you some of the stuff we can do here. If anybody is interested in machine learning, I think some of the stuff we'll see later with the bias conjecture is beautifully positioned for problems in machine learning, where I think they might be able to sniff out the patterns. All right, so classical random matrix theory. I don't know how much physics people know. I was actually trained in number theory from a nuclear physicist who was sick and tired of having so few data points. He would have on the order of 1,000. When he looked at and saw that the number theorists could have millions and billions of zeros of the Riemann zeta function and see similar stuff, he was just amazed. And so I actually learned my number theory from a nuclear physicist. So classical mechanics, Frank Furch. He was one of the original experimentalists behind the stuff that led to the random matrix theory models in nuclear physics. So I actually worked in a nuclear physics laboratory. I have programmed in Fortran. So in classical mechanics, if I give you 1 point mass in gravity, very easy to describe what happens. 2 point masses in gravity, very easy to describe what happens. Sadly, it's not by induction. 3 is no. Once you have 3 point masses in general configuration, we can no longer write down in closed form and extract a nice output as to what happens. Well, if we can't do 3-point masses in general configuration, imagine what it's going to be like with heavy nuclei like uranium, with over 200 protons and neutrons. So in a situation like that, how do we handle something like that? One of the best quotes I ever heard is to try to describe how a nuclear physicist would understand how a grandfather clock works. What they would do is they would take two grandfather clocks, accelerate them to about 99.99% of the speed of light, smash them together. Apologies to anybody who's sleeping, but it's early in the talk, and look at what comes out. And they would use that to try to deduce the internal structure of the grandfather clock. This is what we do in nuclear physics. This is actually what we do for the Riemann zeta function. There is an analog of smashing things like this. And so the nuclear physicists, they shoot neutrons in. And the neutrons they can shoot have given energy bands. And based on the observations, they get some information about the internal structure. Now, everything comes down to the following linear algebra equation to understand quantum mechanics, where H is some matrix, the entries depend on the system, En are the energy eigenstates. The only reason we don't do this in a linear algebra class is that typically H is infinite by infinite, and normally in a linear algebra class, you don't deal with infinite by infinite matrices. And second is we don't know any of the entries of H. And so it's a little bit much to ask undergraduates to diagonalize an infinite by infinite matrix where you don't give them any of the entries. So Wigner's great insight was to basically take some inspiration from statistical mechanics and say, look, don't write down a specific matrix. Look at a family of matrices and try to figure out what's going on for a typical matrix, and then cross your fingers and pray that most matrices are close to the system average. If you want to calculate a quantity such as pressure, you would see for each configuration of your molecules, what's the pressure at a specific moment in time, average over everything. Most of the things will be close to the system average. And that's what's really going on in nuclear physics. And so classically, people looked at, say, real symmetric matrices, complex emission matrices. Later, they moved into classical compact groups. And you can put a probability measure on each matrix element that's independent. The probability of a matrix is just the probability of each entry multiplying through the independent ones. And so the probability that you're in an interval would just be integrating over the interval for each entry. And we want to understand the eigenvalues of A, but it's the matrix elements we get. So we need some kind of formula to relate from the eigenvalues of A to the entries of A and vice versa. Well, the way we get a handle on things is we put a point mass at each normalized eigenvalue. So you always need to figure out what is the correct scale to study a problem. For this, it turns out it's the square root of the size of the matrix. And then if we just integrate the counting measure from A to B, we just count how many normalized eigenvalues are in the band. And then if we calculate the kth moment, and you can begin to see why there's a prayer, you see that the kth moment of the eigenvalues is just the trace of A to the k. So this is the eigenvalue trace lemma. If your probability distribution is nice, if you know the moments, you should know the distribution and vice versa. And so there is a hope that we can use this to understand. And so Wigner was able to prove that if you have a nice real symmetric matrix with entries independent, identically distributed, yada, 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 a typical matrix will have its normalized eigenvalues close to a semicircle. And there's a lot of data on this. So, I looked at 500 matrices, Gaussian, and if you have really good vision, you could actually see there's a red line going almost perfectly through the blue histogram bars. Really good fit. The next slide is choosing the matrix elements from a Cauchy. So one of my conditions was, mean 0, variance 1, the Cauchy. You can argue whether or not it has mean 0. I'll go either way on that. But it clearly, the Cauchy distribution does not have finite variance, and you see very different behavior. So I mentioned earlier that the key result is the eigenvalue trace lemma. When I teach linear algebra, I really emphasize why this is so important. It allows us to get from the eigenvalues to the matrix elements and back and forth. And we'll see in just a few moments an analog of this to do number theory. Sure. So Wigner's law is that as long as your matrix elements have mean 0, variance 1, and finite higher moments, then for almost all matrices as n goes to infinity, the normalized eigenvalues, the spectral measure converges to a semicircle. And this is why we divided by 2 square roots of n and not square roots of n, so we can say semicircular rather than semi-elliptical. The 2 doesn't really matter that much. It's trying to figure out why is it square root of n. And again, I'm doing this for 2 reasons. One is I was trained as a physicist. I like talking about physics. but two, it's a lot easier to describe the stuff here and give you a sense of what's going on in number theory. And then you can go roll up your sleeves and do the more challenging computations in a few moments. Okay, so to just give you a sense of why things are true, I can do this really easily with random matrix theory. So the trace of A squared is the sum of the squares of the eigenvalues. If A is real symmetric, the eigenvalues are real, so these are all non-negative numbers. Not strictly positive, non-negative after the talk earlier today. So the trace of A squared is just going to be the sum of Aij, Abi. If the elements are mean 0, variance 1, each Aij squared is essentially the variance. Each one is of size 1. That should be of size n squared. So the sum of the squares of the eigenvalues is of size n squared. So each eigenvalue is of size square root of n. So the central limit theorem gives me what's the correct scale to study things as n gets large. And then I'm not going to go into the details, but then it just becomes a lot of interesting combinatorics to calculate stuff like this. And so I'm happy to talk more if anybody's interested. This is not a random matrix theory talk. The combinatorics become quite involved. And what you can do is you can look at different types of matrices. So I mentioned the classical compact groups. These occur in a lot of number theory, but you could also look at maybe Toeplitz matrices that are constant along diagonals. You could look at circular matrices. And depending on the structure of the matrix, you will get different combinatorics, which lead to different results, which lead to different spacing measures. And so that allows me to go into the part of the talk that I really want to mention as a preamble to the bias conjecture, the checkerboard ensemble. So because I have so many students year in, year out, I have to have lots of problems. So I have to keep finding new ensembles to look at and hope that, that summer they'll find something interesting. And if not, well, it's been a couple of weeks of their life. They still got a good experience from it. They still learned good techniques. It's not their PhD thesis, it's not too bad. And so one summer we looked at checkerboard ensembles. And so what we did here is we took, real symmetric matrices, and then we put a common weight every so many spaces. So this would be a 3 checkerboard. So every third entry, we put a W. And maybe we'll make W equal 1. And then we can ask, what does this do to the behavior of the eigenvalues? And we saw something really interesting. So all of a sudden, most of the eigenvalues were of size square root of n, but there was a small blip. And the number of elements in the blip was related to the periodicity of how long did you have to go before you got the next W. And as you let the size of the matrix grow, the bulk was of size root n, the other stuff was of size n, and you can see the blip is marching down, marching down, marching down. And so what I love about this is trying to figure out how can you deduce the behavior of what's going on in the small blip. In the limit, almost no eigenvalues are here. Almost all the eigenvalues are here. But if you try to do something like the method of moments to try to understand the behavior, because these are of size root n and there are n eigenvalues, their contribution is actually drowned out for the higher moments by the finite number independent of n eigenvalues here of size n. So these small little eigenvalues completely overwhelm the bulk. And it becomes really hard to analyze what's going on. And so one of the nice tools we have is different weight functions, where you can try to localize what's going on to different parts. And so here, looking at x to the 2n, x minus 2 to the 2n, you can see, okay, well, this is going to be very large when x equals 1. And as soon as I get away from that, it's going to be pushed down. It's going to be 0 at 0. It's going to be 0 at 2. And so this is a way to just localize and study what's going on in the blip and remove the bulk. And then I can play games to get the bulk and not the blip. So you have to develop functions like this so you can figure out how to investigate these different places. This is zooming in, looking at very high values of n for the weight function. And you can see that it's really becoming a spike, and it's only going to detect what's going on there. No, this is, I'm multiplying the eigenvalue spacing measure. I'm weighting the eigenvalues by the value of the weight function at the eigenvalue. And so by doing it like this, only the eigenvalues that are now near 1 will contribute. So if I divide all the eigenvalues by n, the ones in the blip will be of size 1, and the ones in the bulk will be close to 0, because they'll be of size 1 over root n. And so this weight function allows me to focus on just the small number of eigenvalues in the blip. And then when you do this, it turns out you can prove completely what happens and what distributions you get as a function of how many spaces you have to go before you get another W. So the main idea here is that in these random matrix ensembles, we can actually see these lower order behaviors and completely understand what's going on. And my goal is to try to excite somebody here to do this for elliptic curves, to try to find some behavior like this. And again, I may be completely off, and if so, I apologize in terms of, is this, worth looking at? But, one of the problems is those few eigenvalues that are in the blip, even though this almost all the eigenvalues are in the bulk, those few eigenvalues completely dominate the behavior. And that's the problem for some of these biases, is the bias coming from just a few elements that overwhelm everything else, or is there a small bias that's shared by a lot of things? And I think a lot of these questions are still open. We know biases exist, but we're not quite sure how the biases fall among the different candidates. And so I'll skip some of the other stuff, and I'll just go to an introduction to L functions. Before I go through the details, you never know who's going to be in the room. Has everybody seen the Riemann zeta function? Everybody knows the basics. Everybody knows the Riemann hypothesis is true. Yes. We normally get at least 1 or 2 proofs each week at one of my journals proving the Riemann hypothesis. Interestingly, we never get a proof for Dirichlet L functions, only the Riemann hypothesis. All right. Lots of interesting connections, but since everybody seems to know this, I'm going to skip this. Everybody knows the Riemann hypothesis is true. Everybody knows you can generalize, and as long as you have an Euler product, we believe the generalized Riemann hypothesis is true. And then, depending on who you are, you either normalize your critical strip to be S goes into 1 minus S, or if you're doing elliptic curves, you might do S into 2 minus S. So that might be more of an accent issue than physicist versus mathematician, or Bostonian versus non-Bostonian. How do you normalize your critical strip? And for a lot of the calculations, I am with the school that always normalizes the critical strip to be S into 1 minus S. Elliptic curves, have everybody here seen elliptic curves? Yes, okay. And so one of the nice things, many nice things about being a postdoc at Brown, you get to know Joe Silverman, and he gives you access to his tech files and images. So you may recognize these images from several of his books. All right, so we know that if I give you an elliptic curve, there is a group law of addition. And the big question is, how many copies of Z can you have? What is the geometric rank? And the Birch-Swinnerton-Dyer conjecture says the geometric rank is equal to the analytic rank, the order of vanishing of the L function at the central point. And so we can build an elliptic curve L function, which is related to counting the number of solutions mod P. We can use that to get local data, and then we can piece that together. And as I mentioned, the Birch-Swinnerton-Dyer conjecture says that the order of vanishing at the central point is equal to the geometric rank. Right. There are lots of reasons why we care about zeros of L functions. Just a couple of standard lists here. Hopefully you've seen most of these before. What's interesting is if you look at the list, we start off with the infinitude of primes to then Chebyshev's bias that most of the time, in quotes, there are more primes congruent to 3 mod 4 than 1 mod 4. Not always, but most of the time. And then you have the Birch-Swinnerton-Dyer conjecture, then you have stuff about the class number. And it turns out that these are all related to more information about the zeros. The more you know about zeros of L functions, the more things you can say about a lot of problems in number theory. And so for the first one, we just need the Riemann we just need that the zeta function does not vanish on the critical line. Then we need a little bit more. We need some kind of error terms, what kind of region about not the critical line, sorry, that it doesn't vanish on the edge of the critical strip on real part of S equals 1. Then if we know the generalized Riemann hypothesis, then we can start getting better things in terms of error terms in the prime number theorem. Then you have the grand simplicity hypothesis that the zeros of L functions are linearly independent over the ratios, because how could they have any kind of relationship? And when you start to assume something like that, it basically means certain flows become uniform on a torus and nothing is accumulating, and that gives you Chebyshev's bias. And if you assume even more, then you get some stuff about class numbers. All right, so I want to quickly give a rough tour as to how we attack these problems. What is the analog we have in number theory to the eigenvalue trace lemma? So when you teach complex analysis, one of the things you should do is teach your students to have a Pavlovian response. Whenever you have a function, you take the logarithmic derivative, and then you do a contour integral. This is just one of the go-tos. So let's take the logarithmic derivative of the Riemann zeta function. And then as everybody knows, we can write the zeta function as either a sum or a product. And this is why when you look at the Selbig class of L functions, I think all self-respect, oh no, be very careful because this is being recorded. This is why many mathematicians insist that an L function have an Euler product, because if it has an Euler product, we can take a logarithmic derivative, and the derivative of a log of a product is, waving hands for everything to converge, the sum of the derivatives of the logs. And so it converts this product to a sum, which is very nice. And then we can take the derivative of the log. We have a geometric series, we expand it out. And then with a little bit of error analysis, only the first term really matters when we do the contour integrals. We then hit both sides by some nice function, let's say x to the s over s, and integrate. On the left-hand side, when we integrate this, we get x to the 1 over 1 from the pole, and with a negative sign, which cancels the negative sign here. And you'll get an x to the rho over rho from every 0. If all the zeros have real part 1/2 in the critical strip, then this will give you something of size, maybe x to the 1/2 plus epsilon, just to be safe. And on the right-hand side, it turns out that the integral of this term is going to be 1 if x is greater than p, and 0 if x is less than p. And so this is a nice way to then count the primes up to x. And so this tells you why, in the prime number theorem, it's easier first to do a small amount of discrimination. You don't count all the primes equally. You weight the primes by log p. Well, we don't have to integrate against x to the s over s. I could put in some other function phi. And if I integrate both sides against phi, I have a p to the minus s. Well, I can rewrite p to the minus s by writing it as e to the negative log p. And now all of a sudden, what I have is a Fourier transform. And I have a contour integral, which is going to give me phi at the zeros on the left. And I'm going to have a sum over the coefficients of my L function times phi hat on the right. And this is the analog of the eigenvalue trace lemma. This is the starting point of everything. And then it leads to expansions like this. This is the expansion for Dirichlet L functions. And we now have these beautiful sums to do. And this is where you now have to do number theory. We now have to execute these sums over families of these Fourier coefficients. And if we can understand these sums, then we can deduce things about the zeros. And the main terms, we know what to do, at least if phi has suitable restriction. And the goal then is, what information do you get from the lower order terms? A lot of it affects the rate of convergence. So if you've done proofs of the central limit theorem, you might have seen the Berry-Essen theorem that relates how quickly you converge to the normal in terms of the third and the higher moments. And so if you think about the central limit theorem, it's truly remarkable. Whatever distribution I give you, if it's nice, the mean is converging to a Gaussian? Well, if your distribution is nice, I can always adjust it to have mean 0 by a translation. Then I can always rescale it to have standard deviation 1. So really, the first 2 moments of your distribution are always 0 and 1 if your distribution is nice. It's only the third moment that shows you anything about the shape, or the fourth moment if you're symmetric. And this is why in the subject of low-lying zeros, it's really only the first and the second moments of the coefficients of the L functions that matter in terms of the main term behavior. The lower order behavior comes from the higher moments of these coefficients. And that's where things get really delicate. And so I'll just briefly talk about the Katz-Sarnak density conjectures to try to motivate why we care about these bias conjectures. So you could care about them just because you find it interesting as to what can you say about counting the number of solutions on elliptic curves. We know in the limit what certain counts go to. How do they go there? Do they go there from below? Do they go from above? Do they alternate? How are they converging? That's a natural question to ask. To me, the reason I cared is my thesis was trying to understand behavior near the central point. And so you could actually use stuff like this to attack the Butch-Swinnerton-Dyer conjecture. Now, if you really wanted to attack the Butch-Swinnerton-Dyer conjecture, you would have to take your test function phi to be the delta spike. We can't do the delta spike because the Fourier transform of the delta spike is the function that's identically 1, which would mean you would have to do a sum of all primes. We don't have the technology to do that. So you take the closest approximation you can and still do the number theory stuff. So I don't want to go into too much detail on this because I want to try to get to the promised algebraic geometry. I'll just say there's a lot of calculations you can do about low-lying zeros of L functions. This is from Odlyzko, where he looked at the 70 million spacings between adjacent zeros, starting at the 10 to the 20th zero of the zeta function. And he compared this to what you would get from looking at the Gaussian unitary ensemble, and it was just absolutely incredible how well they fit. And so incredible agreement with theory. And so I'm going to skip the n-level correlation stuff. If you've seen it before, then you know it. If you haven't seen it before, it's not really worth going into for a couple of minutes, but it's there on the slides if you're interested. What Katz and Sonek realized, and Rudnick and Sonek realized, is that a lot of these early results about low-lying zeros, they were looking at zeros far away from the central point. And if you take any L function, then the spacing between zeros gets smaller and smaller and smaller the higher up you go. So one L function gives you enough to average over. Well, given that I'm in a place that should care about algebraic geometry and things like the Birch and Swinnerton die conjecture, we don't really care about what's going on high up. We care about what's going on at the central point. And unfortunately, all of these statistics are insensitive to finitely many zeros near the central point, and those are the ones we care most about. So the goal was to find a new statistic that would be sensitive to what's going on at the central point. And this is where Katz and Sonek came up with the n-level correlations. And before they did that, Rudnick and Sonek had noticed that basically all L functions look the same if you go really high up. It's near the central point that you'll start to see differences. And so the statistic they looked at, the n-level density, is basically take some nice test functions, G1 through Gn, we scale the zeros by the log of the conductor, and sum over all the zeros where I don't allow any index to be plus or minus any other. And this is just so that the combinatorics works out and becomes something nice. As soon as you see something like this, you can say, but I want to sum over all the zeros. I don't want to have a restriction like this because when I use the explicit formula, I get a sum over all zeros. So this is basically saying you're going to have to just roll up your sleeves and do some inclusion exclusion. And by doing this, you end up getting a nicer result at the end of the day. And what they noticed is that when you looked at this statistic, now because the G's are Schwartz functions, they rapidly decay. It's only the zeros near the central point that really contribute. And the further you go, the less contribution you get. And the hope is that if you average over similar zeros from similar L functions, that you might be able to extract an average. And so I'm not going to be able to say anything about a specific L function, but I might be able to say something about a family of L functions. So I can't prove the Birch and Swinnerton die conjecture. I really wish I could. But what I can do is I can say, I have a family that has geometric rank 6. And I can show that it behaves as if it had 6 zeros damn close to the central point. And by damn close, I can even quantify what I mean by damn close. I can say, what window am I guaranteed to find the 6 zeros? And the window is not nearly as small as I would like, but I can say in some window, I will be guaranteed to have 6 zeros near the central point. So we can prove results like that. And so the conjecture that Katz and Sonek made is that these n-level densities converge to exactly what you would get if you looked at the eigenvalues near 1 of classical compact groups. And that by looking at function field analogs and looking at monodromy groups, it even tells you which classical compact group it should be. There's some subtleties and there's some other families that arise, but at a high level, this is what's going on. Zeros near the central point look like eigenvalues near 1. And so it's a real challenge to extend support. There was a recent breakthrough where a group of friends of mine were able to get support up to -4 for the 1-level density. And then I thought this would be a great project for my students over the summer to try to do this for the 2-level. And it was a much greater project than I expected. There were a lot of incredibly challenging difficulties that arose when you tried to get to the 2 and the higher level density. And a lot of stuff happened that I was not expecting. And so with the 1-level density, things are often not so bad, but interesting new features emerge when you go to the 2 and higher. Fortunately, for a lot of things we're doing, the 1-level density is enough, but just putting that out there. I was going to skip this, skip that, and then I'll just end very quickly with the following conversion table from physics speak to number theory speak. In number theory, we look at zeros of L functions. In nuclear physics, you look at energy levels. In nuclear physics, you shoot a neutron in and see what happens. In number theory, we shoot a Schwartz test function, and we look at the explicit formula. Now, in nuclear physics, we would love to shoot a neutron of arbitrary energy, but we can't. And so because we can only shoot in certain neutrons, we can only get certain information out. In number theory, we'd love to shoot in an arbitrary Schwartz test function. In fact, something converging to a delta spike. We can't do that. We can only calculate the sums that arise over primes for test functions of suitable restriction on the Fourier transform side. And so that is the analog of the neutron support. So, this is truly how I view number theory. All right, so we've now seen enough language to hopefully have an appreciation of why you might care about the bias conjecture, other than just you like to look at elliptic curves. So what is the bias conjecture? So let's look at a one-parameter family of elliptic curves. So A of t, B of t, nice polynomials with integer coefficients. Every time I specialize capital T to an integer t, I get an elliptic curve. And I can look at the rth moment, and I'm not going to normalize by dividing by 1 over p. I'm just going to look at the coefficients counting the number of solutions mod p essentially, and just raise that to the rth power. And so I can look at I equals 0, I can look at I equals 1, I equals 2, I equals 0 is pretty easy to study, yes? This is just seeing who's awake because it's the afternoon, right? So I equals 1 and I equals 2, those are the first two moments. Those are the ones that drive the main terms. I'd love to be able to understand I equals 3 and I equals 4. And we'll see very shortly why we can't, unless somebody here has a really good idea, which I'm hoping somebody does. All right, so the first moment is related to the rank of the family of elliptic curves. So there's a nice result due to Rosen and Silverman, which basically proves a conjecture of Nagao, which is true in situations where Tate's conjecture is true, which is true for a rational surface. I apologize if I've forgotten anybody who works in algebraic geometry. I think I've hit almost every name with just the slide over here. But in many situations, this is a theorem. In other places, it's a conjecture that if I look at this weighted average of essentially the first moment, this converges to the rank. One of the things I did in my thesis was I actually used this to construct families of elliptic curves of moderate rank. Is I looked for families where I could compute this exactly, and where it was a rational surface, and then I now know the rank. And so I was actually able to construct families of rank 6, 7, 8. I can't remember if I got higher than 8, but around that was where the method breaks down. But it was a nice way to find families of elliptic curves with moderate rank without using specialization, without writing down height determinant matrices and checking to see the points were linearly independent, just by doing analytic sums. So this is what the first moment tells us. So this should hopefully be a motivation as to why we care. And what this is saying is this small negative bias here, which is leading to the rank. And so the bias is important in these sums. And so Michel proved that as long as J of t is not constant, then the second moment is of size p squared, and then the correction terms of size p to the 3/2 p, and so on and so on. And there's cohomological interpretations for what these are. I actually found in my thesis a family where the other term was exactly of size p to the 3/2, so you can't do better than what Michel had, that there are families where it is as large as p to the 3/2. And so in every family studied before July 2023, the largest lower term in the second moment expansion, which does not average to 0, is on average negative. So I'm very impressed that I phrased it carefully when I was a graduate student. So I gave myself some wiggle room. I'm not saying for every prime. I'm just saying, I'm not specifying exactly how I'm averaging. And so just whenever we looked at families, maybe the p to the 3/2 term averaged to 0, but the p term had a negative average. Maybe not for all primes, maybe for some primes it was positive, but then it was more negative for the other primes. And so I told my students, I'm presenting at a conference, this is the date and time I'm presenting. Anything you get to me, say 1 hour beforehand, I will talk about. And can you find a family with a positive bias? Right? And so why do we care about this? Well, it turns out that these lower order terms in the second moment are related to things such as excess rank and bounding rank in families of elliptic curves. When you go back to the Katz-Sarnak density conjectures and you put this in, this actually gives you correction terms. And these correction terms vanish in the limit. But for small conductors, they actually do explain a little bit of excess rank. The amount of excess rank they explain is so little that no major school called me up to give me a full tenured professorship out of graduate school. The amount of explanation is very small, but it does explain a little bit of the observed excess rank. And it gets smaller and smaller and smaller as the conductor gets larger and larger and larger. So we were only able to prove results for very special families where we could compute these second moments explicitly and then just observe them. Well, most families of elliptic curves, you can't calculate the APs when you average over the family explicitly. And so we don't know what's going on for generic. This is, again, why I'm hoping somebody here gets interested. So I mentioned the connection to excess rank. Just when you look at the expansions coming in over here, you can see that there's a term involving the second moment. If you then plug in what the second moment is, you then get a contribution. All right, so just to give you a sense of the techniques that we use, you can use the Legendre symbol to write down a formula for counting how many solutions there are mod p. So the Legendre symbol is 1 if it's a non-zero square, 0 if it's 0, -1 if it's not a square. And what you would expect is, well, if I choose a random cubic, half the time essentially it should be a square and has 2 roots, half the time it should not be a square. And so I would expect that as I vary x, p halves of the time I get 2, I expect the sum to be of size p, and then square root cancellation sounds good. I would expect fluctuations on the order of square root of p. And this is Hase's theorem that the sum is of size square root of p, but heuristically this is exactly what you would expect. Okay, it turns out we can sum linear and quadratic sums very well. And this might remind you of the physics we did, the one-body problem, the two-body problem, and then things completely break down at the three-body problem. Linear Legendre sums are trivial. Quadratic Legendre sums are trivial. Cubic Legendre sums, well, that's an elliptic curve coefficient. That's counting how many solutions there are mod p. We can't write down a closed form expression for that in general. And so unfortunately, when we're trying to analyze things, the only thing we can analyze are linear and quadratic Legendre sums. So the hope is when we're trying to calculate these second moments, we basically do a trick from multivariable calculus. When I teach multivariable calculus, there are 2 things you can do. You can change the order of integration, and you can change variables. And so we change the order of integration. So we have a sum over t for our family, and then we have a sum over x and a sum over y. We do the t sum first and hope that we can use the linear quadratic sums for that, and then have a nice double sum in x and y that have some specialization that happens and makes those sums actually tractable and no longer cubics. Okay, and so I'll skip this. I did not try to make anything small, but just as an example, you can use this to explicitly construct families of elliptic curves with modest rank. This was the least amount of work I could do to make a rank 6 family without writing down any points, just by writing down sums that I knew would have the right value. All right, so here is a table of a bunch of families of elliptic curves. So the first one is looking at all elliptic curves. The next 2 have JFT constant. That's why Michel's theorem is not true, but it essentially is. It's 0 half the time because of a trivial change of variable you can do, and then the other half time you get twice p squared. And then what you notice is in every family we look at, there seems to be a bias. There seems to be the first term that doesn't average to 0 seems to be negative. So over here, I particularly like this family. So N32P is going to be the number of cube roots of 2 mod p. That's clearly not going to be a negative number. It's either going to be 0 or something positive. So sometimes it's going to be positive. So this is going to be definitely something that has a negative average. And C3 halves p, if you look over there, it's p times the sum of x mod on p, 4x cubed plus 1 on p. Oh, well, 4x cubed plus 1 on p, this is basically just the coefficient from an elliptic curve with complex multiplication. We know what's going on here. This is going to average to 0. So this term will average to 0. And I am seeing a negative bias here. Unfortunately, when you try to do any numerics, and this is why I was begging the organizers, and they were kind enough to let me talk about random matrix theory in the beginning, we have the same problem here. We have a term of size p to the 3 halves, which is extremely loud and blasting at full volume and drowning out the lower order terms. So when you try to do numerics and see, this is like looking at the fluctuations in my bank account while my numbers are being added to Elon Musk. And it's going to be very hard to see any differences in what's going on with me with his finances. That's the issue we have going on here, is trying to isolate something like that. So, as an example to give a sense of what goes on, let's look at the family x squared x plus 1 plus x plus 1 times t. Obviously, this is not a randomly chosen family. If I try to calculate the first moment, I have a sum over t, a sum over x. This is not that bad. If I do the sum over t first, I'm going to get 0 unless x times x plus 1 is 0. So then I just have to reduce to when x equals 0, when x equals 1, do those two cases. And it's not too bad. Otherwise, I can just do a simple change of variable. So the first order sum is trivial to do for something like that. For the second moment, it's a little bit more involved. I have my sum over x, my sum over y, and then my sum over t. But notice, as bad as this is, it's just a quadratic in t. So doing a little bit of change of variables and playing games and pulling things out, I now have a really nice quadratic in t sum that I can do. And so nobody wants to see algebraic details in public, but just trust me, if you roll up your sleeves, it's not that bad to execute something like this. And so we have a large number of families where we can play games like this, and we can evaluate things exactly. And when the dust settles, we can get nice closed form expressions. This is one of the things that makes me feel that this could be amenable to machine learning, that there may be nice polynomial formulas that work for maybe not all the primes, but maybe for a lot of the primes, depending on what p is congruent to modulo powers of 2 and 3. So there could be some games like that that you could play. It might also be that there could be other coefficients here, maybe coefficients coming from other elliptic curves. We saw that there was a coefficient coming from elliptic curves with complex multiplication. Maybe some of the lower order terms involve something like that, or other things from other L functions. There's a finite space of interesting examples that could be feeding in. And so with the computers able to check millions and billions of things, I do think that this is a very amenable project for somebody who knows how to do machine learning, which sadly is not me. You can do more involved families. I don't want to go into the algebra in too much detail. There are some lots of fun games you can play in terms of writing things in terms of exponential sums. Anybody who really wants to, the details are at least on the slides, which I have posted on my webpage. I'm always, of course, happy to chat. Don't want to go through all those calculations. Lots of families we looked at. This might have been the year Jared was working with me when we proved this. It might have been around his time. I can't remember now. Lots and lots of formulas. So, in the last couple of minutes, I want to get to roughly, the state of the art. Where are we today? So in 2013, my students were intelligently going through possibilities, and they looked at this family, x cubed plus x plus t cubed. And so here are some plots. The left is a random set with bias 0, and the right is a random bias with mean minus 1/10. And I debated having these slides without those super captions and just asking, does anybody see a difference? And it's really hard to see a difference like that. This is the challenge, is when you have data, can you find the right way to look at it? So looking at this, I think everybody can see that there seems to be some collection of points that have some interesting behavior. Yes? That maybe we should extract whichever primes those are. And so if we look at the primes congruent to 1 mod 3 and the primes congruent to 2 mod 3, we see very different behavior in those two sets. And it comes down to some of the change of variables you can do to x cubed plus t cubed and still get the same thing. And so when p is equal to 2 mod 3, sending t cubed to t is an automorphism. And so playing games like this really helps things out. And so the resulting sums become quadratic. We can execute things exactly. We can figure out what's going on. And so when we look at what's going on, we see, as I said, these plots. And now looking at what's going on for the primes 1 mod 3, it does look like there's a negative bias. And it looks like there might be a large enough negative bias here to overwhelm the slightly positive bias in the other case. We don't know for sure. So for this family, we don't know for sure that there is a negative bias. We've done some looking with running averages. Most of the time, it does seem to be negative, but it does pop up ever so slightly. And then a lot of times you can say, well, what happens when you do something like this? How do you want to justify things? Maybe most of the time, something like that could be the way to look at it. Maybe some kind of analytic density rather than natural density. But again, the real hope is to try to understand generic families. So that was 2023. So now briefly 2024 is I was tired of having all of these small examples, and I mean small not in terms of the small REU, but just specific specific non-generic families. So I said to my students, let's step back and let's create a database of just all possible values. And then once we pre-compute that, which will take a while, now we have the database, and now whatever family you give me, I specialize, and I can just go to the data files and read them in, and then I can look at any family I want to very quickly. And then we can investigate a large number of families, and then anything that looks interesting, we can investigate in even greater detail. One of the things you have to be careful about is I do a lot of baseball mathematics, and there's a lot of discussion as to whether or not there's such a thing as clutch hitting. Well, if there is no such thing as clutch hitting, if you have enough people, just by the law of the central limit theorem and averages, some people will occasionally look good and clutch, even if they're not good in clutch. You'll just have some people who just get lucky. A rare event happens with enough repeated trials. And so we started to just investigate a large number of families. And once we did the pre-computation, we could investigate any family very quickly, because once we specialized, we had already pre-computed what is x cubed plus ax plus b. What is its value for a given prime p for huge numbers of primes? We had that all saved. And now I just have to keep specializing, and I just pull the stuff out. And so we computed a lot of these. We threw away the p squared. We divided by p to 3 halves. And we tried to look at what was going on. And we looked at families where we kept the degrees of the polynomial small and trying to see, do we have some possibilities of examples with a negative bias or a positive bias? So here's a family that we knew had a negative bias. When we do the experiments, we see that, yes, there's a negative bias. And we did it both unweighted and weighted by log p, because we know we should not count all primes equally. We should have a small amount of discrimination. And then here's a family where we're now sampling the coefficients, IID from 0 through 9, and it looks like there might be a small positive bias. But again, we're looking at a large number of families, and so a couple ones could occasionally come up, but it seemed to be large. But again, are we going far enough? And so we started looking at lots of different families, and again, the more families you look at, the more likely you are to start to find stuff like this. We started looking at families where we just chose the coefficients to be either, I think, 0 or 1, to just really keep the list small. And again, it's occasionally positive, but most of the time it seems to be negative. And then you have something like this, where this one seems to be significantly above 0 for large regions. Is something happening for this family? Can anybody who really knows algebraic geometry and counting things on points, I am happy to personally email you the slides. Is there something going on that would allow us to count how many solutions there are and get some kind of bounds? We know that the second moment is p squared plus a correction. Do we have some idea of how it's converging to the p squared? Is there a bias in which direction it's coming from? Here's another one. And again, we're just choosing the coefficients to be 0, 1 for the polynomials to just keep things nice. You notice things like t squared minus t plus 1 are sometimes in blue. These were polynomials that were occurring a lot. Is there something going on as to why those polynomials are occurring? Another family again, t squared plus t plus 1 coming up again, t squared minus t plus 1 coming up again. And again, families like this, they're staying positive over significant regions. But again, significant regions, I'm looking at primes up to 250,000. And with a large number, rare events should happen occasionally. What happens as we go further? So again, I can keep showing you lots of different examples. Looking at enough data, I can definitely find 10 or 12 examples. That's not hard to do with this much data. Is something really going on? Is there a reason we keep seeing some of the same polynomials coming in as factors? Is this an indicator that something's happening? So this is a great opportunity for data to suggest what might be worth investigating. So I'll just end with, a bunch of references. If anybody's interested in looking more, there's a bunch of links on this, and just, thank you. Yes, so if you email me, happy to share the data.
Have you noticed any patterns besides just like any patterns of properties in the
No, I wouldn't be surprised. And then my students have also, now that we have the data and we've given up on proving theorems, we can now look at the third, the fourth, the fifth moments. And I'm going to stop recording now because I can speak a little bit more freely.